Hello, good afternoon, Clarence, Lynette, Z, Christian, Jehan, and I think it's Stevens. So, yeah. So today, I think this is the last session for, yeah, good afternoon, Peter. This would be our last session for Unit 2B, which is basically talking about data science tools, specifically in linear algebra. So I'll just finish it off with a discussion of the pseudo-inverse and regularization techniques. Okay. Now, just a quick recap. In the last two sessions that we had, or basically this whole section is devoted to finding solutions to linear systems that are large in nature, right? And how to handle them efficiently and accurately inside a computer. So we did LU decomposition, which we said is a nice generalization of the Gaussian elimination that we all knew from elementary or high school algebra. But the problem is that it's only applicable whenever we have a square matrix. Though I know there's an extension to non-invertible matrices, but we are not guaranteed to always have an LU decomposition for arbitrary matrices, right? The only result that we have is that if your matrix is invertible and all of the minors are non-zero, then we are sure there's an LU decomposition. Now we look at another method, which is the QR decomposition, which offers the existence of a factorization for matrices or for all matrices, right? So all matrices admit a QR decomposition. And the nice thing about the QR decomposition, it frees us up from the very costly process of computing the matrix inverse, right? Although there are several ways to implement the QR decomposition, some are, or theoretically, all of them will give you the same QR decomposition, but or up to scaling constants. But when you use them or when you implement them inside computers, you need to be very careful because QR decompositions are usually very prone to numerical instabilities or to errors due to machine precision, right? So that's why I skipped the classical and the classical QR factorization because it employs the classical Gram-Schmidt process, though a very powerful theoretical tool, but in applications it's highly unstable because the ordering of the operations is not optimal in such a way that we are minimizing the number of operations because when you do computations inside computers, there would be truncations every step of the way, all right? So we are avoiding those truncation errors to pile up. So that's why we need to be very careful in how we order and how we group the operations, even though they are just arithmetical, but the finite nature of machines will really introduce these errors that easily piles up in the end. Now, that's why we had a householder algorithm, which is a stable and a nice QR factorization method. And this is usually employed whenever dealing with large systems, especially those arising in data science. So you do QR decomposition because after the QR decomposition, the problem reduces down to a backward substitution problem, right? After you have your unitary matrix Q, then you translate your matrix into the system R Rx equals Q transpose times B, and then use this using forward substitution, right? And there's no matrix inversion involved because the way we select the factor Q, the factor matrix Q is that this is unitary, or in the case of real matrices, this is called an orthogonal matrix, such that Q transpose is equal to the inverse of the matrix Q. So we don't have really to go through the expensive process of computing Q inverse because we can compute Q inverse lexicographically. That's a nice property of the matrix Q, right? Now, we have seen last time an illustration of how QR decomposition might help us in solving rectangular systems. But in that solution that we had, I think the error that we got is 50%. This is basically the residual between AX. A is your coefficient matrix. X is our solution from the householder algorithm minus the target right-hand side. and then I divide it by the size of the target right-hand side, right? And this, I think, is equal to something around 50%, right? And we're wondering, is this the best that we can do, right? Now, another algorithm or another method to solve rectangular systems will be to deal with the normal equation. Remember, if you start with a rectangular matrix, a rectangular system, AX equals B, what we do is to multiply both sides, say, by the transpose of A. And then we are hoping that A transpose A is invertible, and usually that's the case. And the other prayer that we must say is that the matrix A must easily be invertible, right? Because otherwise it will be still a very costly process. And if all of those things happen, then we can say that X is equal to A transpose A inverse times A transpose B, right? So basically, this is the least square solution to the system AX equals B, or in other words, this is also called the normal solution or the normal solution, right? Now, there are several things to note here. This approach is very much suitable for data science problems, or in problems even if whenever you're dealing with large amount of information, wherein the number of equations or observation points that you have is huge compared to the number of unknown parameters in the unknown vector x. So for instance, in this case, we are saying that A, for instance, is rectangular of dimension m by n, right? And again, for our purposes, the number of data points that we have or observations points that we have is much larger than the number of unknowns. So in that case, m is much greater than n, all right? Now, if you look at the dimension of this matrix, right? The matrix A is m by n, the matrix A transpose is n by m. So essentially, we are taking the inverse of an n by n matrix instead of dealing with the tall but thin matrix A, right? So we're going to have a smaller square matrix. And again, this smaller square matrix is often invertible. So that reduces the complexity of the problem by a huge amount, especially if m is really much greater than or equal to n, all right? So essentially, this is the very foundation of what we know to be the pseudo-inverse of a matrix, and that's what we will discuss today. There are several reasons why the pseudo-inverse is important. The most obvious one is that we know that not all matrices are invertible. In fact, only a fraction of square matrices are invertible, right? And again, matrix inversion is quite costly, right? So that's the other reason. So there is a question, how can we generalize the concept of the inverse of a matrix? So can we define, or can we build up a theory that allows every matrix to have some sort of the notion of an inverse? And that was the proposition broached by three mathematicians. I just forgot their name. It's Hastings Moore, Arne Bianhomar, and Roger Penrose. So we'll be talking about what usually is known in literature as the Moore-Penrose pseudo-inverse. There are several attempts to generalize the concept of the inverse, but I guess the most popular one is the pseudo-inverse, which is used in data science and inverse problems. So the Moore-Penrose pseudo-inverse. So again, the motivation behind this concept is again solving systems that have a coefficient matrix that is not invertible. Or in general, you have AX equals P that is rectangular, for instance. It's an m by n matrix, right? Now, there are two possibilities here. The one possibility is that the system is underdetermined, meaning there are more unknowns than the number of equations. So that, for instance, you have this system over here, right? It's what? We have two equations, but three unknowns. Our matrix here, our coefficient matrix is 2 by 3. It's underdetermined because we have more unknowns than the number of equations. And underdetermined systems will either have a solution or infinitely many solutions. In particular, this example that I have doesn't have any solution. All right, and it's easy to see that that this cannot have a solution because look at the rows that I have over here; they are just the same, right? But if you have this, so if I write this as x1, x2, and x3, if I get a solution x1, x2, x3 to the system, then I'm saying that x1 plus x2 plus x3 is equal to 1, using or multiplying the first row by the column, right? And the right-hand side is 1. But if I'll do the same thing, but with the second row, I'm going to have x1 plus x2 plus x3 equal to 0, which directly contradicts the previous statement. So indeed, this underdetermined system has no solution. Now, meanwhile, this other system still underdetermined, but it has an infinitude of solutions, right? So you can, this is a small system, so we can try to solve this manually, and we will get the following form for the solution, all right? So you just give your choice of x2. So say I choose x2 to be 3, the second component is 2, so the first component will be -1 minus 3. So this would be -1 minus 3. That's going to be -4. So this is a solution. And then you pick another x2, you will get another triple of solutions. So that's why you have infinitely many solutions. All right. So that's the thing that's happening with underdetermined system. The same thing can occur for overdetermined systems, which is basically what we will usually encounter in data science, statistics, or inverse problems. Right? So we have more constraints represented by the equations than the degrees of freedom represented by the size of the unknown vector. Right? Now, so today, as I've mentioned, we'll be working with the Moore-Penrose pseudo-inverse, and we look at its different properties, right? And why is it a nice generalization of the concept of the inverse of a matrix, right? So here, just a recall of some notations, but I hope these are still fresh on your minds. We start with a matrix A with entries represented by A sub ij. Again, this means that the entries in the matrix are represented based on the row number I and the column number j. I goes from 1 to m, the number of rows. J goes from 1 to n, the number of columns. In this text, I am considering matrices whose entries are all complex numbers, but there are some instances that we are fine whenever they are just real numbers. So we can just adjust along the way. And some necessary concepts again. The transpose of the matrix is just the reassignment of the position of the entries. If your original entry lies on the first row and the jth column, then in the transpose of the matrix, it will be on row number j and column number I, right? And so the dimension of A transpose will also be different from the dimensions of the matrix A. If your matrix A is m by n, then the matrix or A transpose would be n by m, right? And then if you're dealing with matrices with complex numbers as entries, you need to be very careful. Everything that uses the transpose of the matrix A should be replaced by the conjugate transpose. All right. So be careful. You need to double check. Do I have non-real numbers in my matrix? Because if that's the case, then you should use the conjugate transpose A star. But if you only have purely real entries in your matrix, then A transpose will be the same as a conjugate transpose. So everything will work out nicely. But I think I promised you that we'll just be dealing with real entries. So whenever you see A star, you can think of it as A transpose. Because again, the conjugate of a real number is equal to itself. All right. Now, our first definition for the night, definition 9.1. This defines exactly what the Moore-Penrose pseudo-inverse of a matrix A is. Now, this is a textbook, not textbook, but probably better called a theoretical definition of the Moore-Penrose pseudo-inverse, because this gives us the identifying characteristic or the distinguishing characteristic of the pseudo-inverse, denoted by A plus. Oh, sorry. So this is our notation for the pseudo-inverse A plus, right? And it is the matrix, or it is a matrix that satisfies the following properties. So here, property number 1, A times A plus times A should be equal to A. Property number 2, A plus times A plus should be equal to A plus. Number 3, the conjugate transpose of A plus should be A plus. And lastly, A plus A conjugate transpose should be A transpose A. So this definition is for theoretical purposes, right? How we prove properties for the Moore-Penrose pseudo-inverse, or when we start checking whether a given matrix is a Moore-Penrose pseudo-inverse of another matrix, you need to check if all 3 properties, or if all 4 properties are satisfied, right? Now, the idea behind the definition of of the pseudo-inverse is really to mimic what A inverse is for invertible matrices. So that means the very idea here is we're choosing the matrix A transpose to act as if it is the inverse of a matrix A, even though the matrix A is non-invertible. So we're trying to get a fake inverse. So that means we want A plus to be approximately equal to the identity matrix of the appropriate size. Right. So this is the target. We want A plus to behave as if it's the identity matrix. And that becomes apparent if you look at the 4 conditions that were laid down in this definition. Now again, we want A plus to yield the identity when paired with A. So look at A plus here. We want this to be as close to the identity as possible, right? So we're looking for the matrix A plus that will give us the right identity, the identity matrix of the right size, so that when I multiply A plus to A, I will get back A. So you can think of A plus to be the identity matrix of the right size, or acting as if it's the identity of this of the right size or right dimensions to get property number 1. Again, property number 2 can easily be remembered. Again, the target is for A plus to behave as the identity, or to become the identity matrix. So that's why A plus times A plus, but we know A plus should behave as if it's an identity matrix. A plus times identity matrix is equal to A plus. And the same thing goes from property 3 and property 4, right? Because the conjugate transpose of the identity matrix is itself, right? Now, this might not make any sense or any help for us right now, because this is highly theoretical. But really the motivation behind this definition is that these 4 things will guarantee that we get A plus times A to be an identity matrix of the right size, say size n, and A plus times A is an identity of size m. Because remember, A need not be a square matrix. So the sizes of these 2 different identity matrices might be different from each other. All right? Okay, so if I ask you to verify that a given matrix is the pseudo-inverse of another matrix, I think there are examples or exercises about that in this module. So you'll just need to check. Plug in A here, plug in the supposed A, the pseudo-inverse of A, multiply it by A, then it should be it should be equal to A exactly. Then you do this for the 4 properties here, and if all those properties were met, then indeed the given matrix A plus is the pseudo-inverse of the matrix A, right? Any questions so far? Yeah, I didn't notice that I had been speaking for 20 minutes already, but any questions? Right, everything's making sense?
So we are fighting.
All right, good. So let's see. The first result And I think this fulfills one of the promises or one of the wishes that we have for the generalization of the matrix, the inverse of a matrix, right? Theorem 9.1 tells us that if you're given any matrix of any dimension, all right, there exists not just a Moore-Penrose pseudo-inverse, but we are sure that that Moore-Penrose pseudo-inverse is unique, right? So we can only find a single matrix, right? A plus satisfying all of these four conditions. So that's nice to know that indeed this is the first step that we wanted, right? Because we want to map the set of all matrices into another set, such that everyone will have sort of an inverse or a pseudo inverse. Now, the nice thing is we know that any matrix will have a partner matrix, A plus, satisfying all these four conditions, and not just that, that pseudo inverse would be unique, right? But of course, we'll skip the theorem. This is not a theoretical course on linear algebra. So just believe me, the theorem 9.1 is true. Okay. Now, yeah, in exercise 9.1, I asked my students, because I'm using this for an undergraduate class. So I asked my students to first verify that a matrix is a pseudo inverse of another matrix. So you can also try doing so, right? You'll just need to check if all these four properties were satisfied, if the matrix A is given to be if the matrix A is 1, 2, is its pseudo inverse equal to the matrix 1, 5, 2, 5, right? So to see that, so you just plug them into these four equations and see if you get an identity, right? So yeah, you can try solving these three exercises. I guess they're pretty straightforward. You can write a short code that will check all those four properties. Okay. And yeah. And then so we are, one of our wishes we're already satisfied. The other one is we want this to be a generalization of the inverse of a matrix. So we know that all matrices have a pseudo inverse. Now, the other good thing about the Moore-Penrose pseudo inverse is that all invertible matrices will have its inverse to be its pseudo inverse, right? So it's as if we are retaining the inverses of invertible matrices and just inventing what is to be called the pseudo inverse for all other matrices. So you can think of the Moore-Penrose pseudo-inverse to be a generalization of the inverse of a matrix in two ways. All matrices will have a pseudo-inverse, and the pseudo-inverse of an invertible matrix is its pseudo-inverse. Okay? Now, the only problem so far that we have in this whole theory that we're trying to build, but before I go there, Z, you have a question?
Yes, sir. About this A plus is equal to A inverse, does it always guarantee that the A inverse can satisfy the properties above automatically for invertible matrices?
Oh yeah, good question. It should, right? So we can take a quick look, right? So yeah, probably that's the proof that if A is invertible, then A plus will be equal to A inverse. Because again, if A is invertible, so we can replace this by A inverse. A inverse is the identity matrix, right? So that's going to be the identity matrix. Identity matrix times A is A. So that's satisfied. Property 2, this will be A inverse. This will be A inverse. A inverse times A is identity. Identity times A inverse is A inverse, right? So that's also satisfied. A inverse is identity. The conjugate transpose is identity. But this guy is A times A inverse, the same identity matrix. So you get identity equals identity, so that's fine. And a similar thing will happen for condition number 4. All right. That was a nice observation, Z. Actually, that's the proof of this remark over here, right? So it really generalizes. Now, the hard thing to prove really is the meat of theorem 9.1, that all matrices will have a pseudo inverse and that the pseudo inverse is unique. Actually, Yeah, I think the second one is easier than the first, all right? But if you're not interested with that, or if nobody would like to prove that, then we can go ahead because that would be in the domain of linear algebra already, right? Now, as I was saying earlier, the only hole in our theory so far is the computation of the pseudo-inverse. Because if you will look back at how we define the pseudo-inverse, it laid down all of the all of the distinguishing characteristics of the pseudo-inverse, but it did not tell us how to compute the pseudo-inverse or how the pseudo-inverse looks like, which is a typical math thing. We in the math profession, or in the doing pure math, we always want a definition that lays down all the distinguishing characteristics, even if we are not constructing what is being defined, right? So here we're talking about the pseudo-inverse. We are telling you what are the properties of the pseudo-inverse, but we didn't tell you how to compute the pseudo-inverse. And then in the next theorem, we are telling you that there exists a unique pseudo-inverse, but again, we are not telling you how to compute them. Because in general, computing the pseudo-inverse of a matrix might be very difficult, all right? But for a big class of matrices, the matrix A plus can easily be computed. And that is what we have in theorem 9.2. In theorem 9.2, we are only checking the invertibility of A conjugate transpose times A, or in the case of matrices with real entries, we're looking at the invertibility of A transpose A and A transpose, right? So if this matrix is invertible, then the pseudo-inverse of the matrix A is A conjugate transpose A inverse times A conjugate transpose, right? If, on the other hand, this is not invertible, this one is the invertible matrix. Remember, these two guys are not generally equal to each other because matrix multiplication is not commutative, but essentially, yeah, if you know this is invertible, then you can compute for the Moore-Penrose pseudo-inverse this way. All right? Most of the times, this is what we are praying to be, this is what we are praying to be invertible, all right? Because this will give us a smaller matrix to invert. Because again, in our field, we want M to be much greater than N, right? A is an M by N matrix where M is much greater than N. So A transpose A, or A conjugate transpose A, will be N by N. But if we do this, our square matrix will be M by N. And surely, computing the inverse of A conjugate transpose is much more expensive than computing the inverse of A transpose A. That's why if you were to choose which one to do first or to try first, we first do this, try it to see if it's invertible. Or we ask our program or computing devices to compute this guy, because if this exists, then that is the unique Moore-Penrose pseudo-inverse for the matrix A. All right? So finally, we now have a closed form formula for the pseudo-inverse, at least of matrices for which either A conjugate transpose A or A conjugate transpose is invertible. Okay? Now, another thing that you can try, because these are just computational exercises, but at least for me, I guess computational exercises are still helpful, even at this level, because for you to really understand the topics and check yourself if your understanding of the previously defined concepts are correct, then try to answer this quick, small and computational exercises just to see how to compute for the inverses. One thing that you can do is try to see if the inverses of the matrices will coincide with the pseudo-inverses. Although I'm thinking now, this matrix is not invertible, this matrix is not invertible, this is also non-invertible, this is obviously non-invertible, this is non-invertible. So I cannot test whether I cannot show computationally that pseudo inverses are equal to the actual inverse if your matrix A is invertible. For this one, yeah, not also the case because this is 4 by 4. But I guess the point of exercise 9.4 is really to show that even, or actually especially non-invertible matrices will have pseudo inverse, which we can compute hopefully with the help of theorem 9.2. Okay. All right, so I hope you do that. And then if you encounter some problems, then I'll be more than happy to help you with that. Right. Now, how does the pseudo inverse help us in solving linear systems, especially rectangular ones, all right, or singular ones? So if we start with a singular or a rectangular one, actually, even if you have an invertible matrix A, it is often the case that using the pseudo inverse is much more computationally cheap than computing the actual inverse of the matrix A. That's why, for instance, if you're using MATLAB, it is much preferred that if you're solving the matrix A, the system AX equals B, you write X equals pseudo inverse. The notation is P inv of A times B, all right, instead of X equals inverse of A times B, right? Even if the matrix A is invertible, because matrix inversion is much more expensive than computing for the pseudo inverse. Actually, since pseudo inverses are highly utilized in MATLAB programming, they define a special shorthand symbol for using the pseudo inverse. So in MATLAB, if you have the matrix A and B defined on your code, then to compute for the pseudo inverse solution, so you just use A backslash B to get the solution using the pseudo inverse. Okay. Now, we have noted earlier that overdetermined or underdetermined systems can have no solutions or will have infinitely many solutions. Now, if your system will have infinitely many solutions, then the pseudo inverse is also helpful in representing all of those solutions. So if that's the case, then we can take advantage of equation 9.3. It is claimed that any solution will be of the form given on the right-hand side of equation 9.3, right? For any vector W of the right dimension. So indeed, the pseudo inverse will not only characterize a solution. It will not only characterize a solution to the problem, but if there are infinitely many solutions to your problem, it can be used to generate or to get all of the solutions to your problem or to your given problem. All right. Now, do you remember when a system AX equals B will have a unique solution? A general, what's one specific case when AX equals B will have a unique solution? Yeah, on second thought, that might be a very a vague question because we're talking about non-singular. We're talking about singular and rectangular systems, right? But remember, just to validate or to have a sanity check with within the theory that we're building here. Remember that yeah, thank you, Jihan. That's what I'm looking for when A is invertible. Remember, because when A is invertible, there's a unique solution, A inverse B. All right. So to the problem, right? And if A is invertible, so this will be A inverse B, right? And then this will be A inverse because the pseudo inverse is also the pseudo inverse. But A inverse times A is the identity matrix. Identity minus identity will be the zero matrix. Zero matrix times any vector of the right dimension will give us 0. So we'll be left with X equals A inverse B, right? So indeed, equation 9.3 covers the cases when you have a unique solution and when you have infinitely many solutions. All right. So the only problem now is how will the pseudo inverse fit in solving systems with no solutions at all? All right. Which when you say those words, it might sound absurd because why are you solving a system that doesn't have any solution? What I mean by solving a system with no solution, I mean by looking for the next best solution. All right, because we don't have an exact solution, but what's the best thing that we can get as a solution to that problem? Well, a common measure is using some norms or some measures of largeness for the residuals, right? So whenever the linear system that you are considering does not have a solution, then we look for the solution vector x star, which we know is not an exact solution because there are no solutions in the problem to be found. But the thing here is that what's the next best thing, right? The next best thing that we're looking for is the vector x star, which is the residual minimizer. That means it should be the vector x that will make ax star to be very, very close to b with respect to some measure or some norm, right? But I guess for this class, we'll just be considering the L2 norm. Again, the L2 norm of a vector is simply the square root of the summation of the absolute values of the squares of your vector, right? Of your vector of solutions, or your solution vector, right? So you take the square root of the sum of the squares. That's the L2 norm. So again, geometrically, we are looking for the vector x star that will make the product ax star very, very close to our target vector b, right? Because we know that ax star will never be equal to b, right? Because we are assuming that we don't have any solution here. So our next best, our only resort is to look for what is the vector x star that will make this measure very, very small or as close to zero as possible, right? Now, if you're into linear algebra or into approximation theory, you will know, you will prove and you will encounter the theory behind the Moore-Penrose pseudo-inverse's nice property, which is it is the residual minimizer. The Moore-Penrose pseudo-inverse will give us the smallest error vector, to be more particular, with respect to the L2 norm, right? So that means we can choose x star to be a pseudo-inverse times b, and it is sure to minimize the L2 norm of the residual. So this will give us the smallest residual among all possible vectors with respect to the L2 norm, right? Now, what will happen again if A is invertible? If A is invertible, then X will have a solution. Will this thing will still work? Because again, we said that the pseudo-inverse is the generalization of the inverse of a matrix. A plus will be equal to A inverse whenever A inverse exists, right? Now, the answer is yes. You will still get the least square solution will still be the unique solution, right? Because if A inverse exists, then X star will be A inverse B, but that means AX will be exactly equal to B, right? Because this is the unique solution. But when AX is equal to B, then AX minus B is the zero vector, and the size of the zero vector is equal to 0. And that's the minimum possible value that we can get. So indeed, everything now seems to be a perfect generalization of solving under or over determined systems. All right. Now we call this solution the least square solution, or we can also call this the Moore-Penrose pseudo-inverse solution, right? But it is more known to be the least square solution. Okay, it is called the least square solution or the normal solution. Yeah, this is another name for it, the normal solution, because it is obtained by solving what is known in linear algebra to be the normal equation corresponding to the given system. If your system is AX equals B, right? If the system is AX equals B, then what we do is to multiply both sides by A conjugate transpose, so multiply both sides. Again, we need to be very careful where we multiply the vector A conjugate transpose, right? So we're gonna get equation 9.5, which is called the normal equation. And solving the normal equation will give us the normal solution. And incidentally, again, in this particular case, we're hoping that A conjugate transpose times A will be invertible, right? And if that's the case, I can multiply both sides by the inverse of this guy to get this, right? Our solution. But remember that this is exactly a pseudo-inverse per theorem 9.2, I guess. Tama ba? That's theorem 9.2. Yes. The Moore's Penrose pseudo-inverse is that guy. So incidentally, the normal solution is also the Moore Penrose solution. Okay. Now, yeah, I mentioned here that this is the closest thing that we can get to a solution of an inconsistent, overdetermined, or underdetermined system. Right? So I guess that's too much of theory, but I guess that's all the thing that those are all the things that we will need for the pseudo inverse. Anything that you want, any questions that you might have about the theory, or you don't care about the theory for now, because we are just after using these to solve big and thin matrices, right? So if there are no questions, let's see the pseudo inverse in action. But I guess we have already seen this in the previous module that we discussed, right? We have a system AX equals B with matrix A equal to this guy, and our right-hand side is 2, 4, 6, 1. In the last module, I noted that B is not in the range of the matrix A. That means theoretically we know that any vector multiplied to this coefficient matrix will never give me, or no vector x1, x2, x3 multiplied to A will give me 2, 4, 6, 1. So we go to the next best thing that we can get to a solution, right? Now, this is a rectangular system, so we won't even attempt to solve this using Gaussian elimination or using matrix inversion. But when we perform the householder QR factorization that we learned last time, what we got is this solution, all right? And then if we want to compute the residual, all right, again, we're hoping to get a small residual, the smallest L2 residual. So if I will compute A times this solution, the householder solution, we will get 3, 3, 3.5, 3.5 transpose, right? I just wrote it this way because it's very, to save some space, because the actual form for X sub H is 3, 3, 3.5, 3.5. I don't want the way it looks in the handout. So this is the product of A times XH. But again, what was our target? Our target was 2, 4, 6, 1. So looking at these vectors, we see that they are quite far from each other. Okay. Now, to really measure, we measure the residual. So we just subtract 2, 4, 6, 1 from this guy, right? You will get a vector. But again, the problem with looking at the residual, of course, theoretically, we want all the entries of that residual vector to be close to 0, right? Or essentially, this is what I want. This vector to be equal, actually, this vector is equal to what? 3 minus 2, so that's 1. 3 minus 4 would be negative 1. Then 6, because 3.5 minus 6, that's going to be what? Negative 2.5. And then I'll have negative 2.5. I hope my arithmetic is, sorry, that's not, 3.5 minus 1, so that's going to be 2.5. 2, 4, 6, 1. I hope my, my arithmetic is correct, but kindly correct me if I'm wrong. I just computed this guy minus 2, 4, 6, 1. Okay. So ideally, so this is what we call the residual vector. The residual vector. And we want the residual vector to be close to the zero vector. So we want this to be very, very close to the zero vector, because if that's the case, then that means we are matching all the entries of the matrix of the vector B exactly, right? But when you're talking about errors, you want to get a sense of how big the error is, right? If you're talking about vectors, it's hard to quantify, is this vector small enough, right? Because some of the entries might be close to zero, some entries might be close to zero, might be far from zero. But how do we say that the residual vector is small? That's why we compute the norm of that vector, right? So if we compute for its norm, so we simply do the L2 norm. So this would be the square root of 1 squared plus negative 1 squared plus negative 2.5 squared plus 2.5 squared. Whatever this number is, that's the L2 norm of the residual vector, right? And we are hoping that that number is close enough, is small enough or close enough to zero. But again, there's a problem in interpreting this kind of data. What if, say, right, let me use a calculator to compute this so that we will have a better discussion about the numbers here. So I'll do this, then times 2 plus 2. Then I'll take the square root. Where's my square root in my calculator? There we go, square root. So I guess, is this right? This is around the 3.81. The residual has L2 error 3.81. So, but again, the question is 3.81 small enough? All right. So, because we don't have any point of reference, we know that that's the size of the residual vector. We want this to be close to zero, but we don't know if that is close enough to zero or not. That's why whenever I need to interpret the error or to compute the error and use this in my analysis, I always compute the relative error to see how big the residual is relative to my target vector, right? My target error vector is 2461. So I'm going to compute for the L2 norm of 2461. So that's going to be 2 squared plus 4 squared plus 6 squared plus 1 squared. Whatever that number is, that will be my denominator. So you will get a quotient or a ratio between the size of the residual and the size of the target vector. And if my arithmetic here is correct, the relative error is 0.5044, meaning the residual is around 50% of the target vector. And that's a bad thing, right? Because we want the residual to be very, very small relative to the right-hand side. Okay, so this is not good. Let's see if we can further improve this, right? Now we can check its accuracy, or if it's the best one that we can get, because now we have the theory to support the existence and the calculation of the least square solution, right? So what is the best solution? What is the best vector X star in the sense of minimizing the L2 error, right? And we know that that would be using the pseudo inverse, right? So that's what I did in the next example. So I am now hoping that A star A is invertible so that I can use theorem 9.2, right? So performing hand calculations here, A conjugate transpose times A is equal to this guy, right? And then inverting it will give us this matrix A star A. And then computing the pseudo inverse via theorem 9.2 will give us this guy, right? And remember, we were told in our discussions above that the least square solution is X equals, or X star equals A plus times B. If you compute A star, A plus B, you will get this vector. Oops, you will get this vector. Negative 6.375, 2.75, and 0.125, which is far from what we got from the householder solution. The householder solution, how does it look like? It is negative 5.625, 2.75, 0.125. and this thing is like that. All right, so they are really different from each other, right? Now, which one is better? We should expect that this will give us a better solution, right? Or a solution that will give us a smaller residual, right? And indeed, if you will repeat all the calculations we did above for the relative error, but using this X star, we will get 0.4636, which is still not that good because you can interpret it by saying that the residual is around 46% of my target vector, which is nowhere good, right? But the thing here is we know that we cannot do any better than this solution that we have, because theoretically it is guaranteed that the pseudo inverse solution or the normal solution will have the minimum L2 norm for the residual, right? So that means we have improved a little bit what we got from the householder algorithm and have gotten this. Okay. But I hope this gives you an idea how to use pseudo inverses for computing the inverse of for computing the solution to a inconsistent system, right? So inconsistent system, so we don't expect to have a solution at all. Okay. Any questions before we go to the next example? All right. No questions. Everything is straightforward. Okay. So let's look at another example and let's see what this will add to our understanding of the pseudo inverse. So again, I have a system AX equals B, but this time it's a little bit smaller because we have a 3x2 coefficient matrix. So this is an overdetermined system, and this is our right-hand side. Again, if you want to find the least square solution, you can simply use the pseudo inverse. If you're doing it by hand, you can compute for the pseudo inverse first. So check if A transpose A is invertible, right? Or you can just, if it's invertible, then compute the pseudo inverse. The pseudo inverse is simply this guy. Multiply that to B, you will get 1, 1. Okay? And we are guaranteed that this is the solution that will give us the least L2 norm, right? Now, incidentally, 1, 1 is an exact solution, because if I multiply this 1, 1 to the matrix A, we'll have 0.15 plus 0.1, 0.25, 0.16 plus 0.1. Oh, hold on. 0.25. Oh, yeah. 0.16 plus 0.1. That's going to be 0.26. Yeah, I got a little worried about that. I messed up the addition of 0.16 and 0.1. They will add up to 0.26. And I have 2.02 plus 1.3. That's going to be 3.32. All right. So 1, 1 is indeed the solution. Now, since the matrix A is not invertible, and we have found an exact solution to the overdetermined system, then there's a possibility that there are infinitely many solutions for this particular problem, right? Because A is non-invertible, you will have a unique solution if the matrix A is invertible, but we know that A is non-invertible, so there might be other solutions. And whenever you are doing, say, if you're solving problems, say, in control theory, looking at all those other possible solutions are also important, because you want to find the most efficient out of those infinitely many solutions, right? So 1, 1 is our candidate because it is one of the exact solutions, but there will be infinitely many of them. How can I find all the others? Well, we can use, that should be the unique solution, by the way, because I was thinking that there could be infinitely many solutions, but we are not sure if there are really infinitely many solutions. How can I check that there are indeed infinitely many, if there are infinitely many solutions, or if there is a unique solution? Well, I'll go to equation 9.3 again, Because in equation 9.3, let me just scroll up. This gives us a form for all of the possible solutions, right? So we know that 1, 1 is a solution and 1, 1 is A plus times B, right? And any solution can be obtained by adding to it this guy, right? So, and it really depends on A plus times A, because W is any vector that you can think of the appropriate size or the correct dimensions, right? But if you go to the problem at hand, A plus times A is actually the identity matrix, all right? Remember the formula for all solutions, X star will be A plus times B. Was it a plus? Sorry, I have the memory of a goldfish, so I need to go back and see what's happening here, right? So I know that A plus times A in our instant problem will be the identity matrix, identity minus identity. This goes to the zero vector as zero matrix rather, times W will be the zero vector. A plus B times the zero vector will be A plus B. So A plus B is 1, 1. So there is a unique solution 1, 1 to this overdetermined system. All right, so that means the pseudo inverse will not just show us the least square solutions, but this will also be a good check if we have a unique solution. Because if you have an exact solution, compute a plus times A, if that's identity, then we have a unique solution. Okay? Right, so I also have some exercises here, so you can take a look at them. All right. Okay. So the only case that we haven't considered so far is when there are infinitely many solutions. So how will the pseudo inverse handle them? Right. So recall this system in our introduction to earlier. So we know that this system is an underdetermined system with infinitely many solutions. And the form for the infinitely many solutions is this guy. -1 minus x2, x2, and 2. So x2 is a free variable. You give any value to x2, you can compute the appropriate x1. 2 is fixed over here, you will get another solution. So using this formula, you can generate all possible solutions to this underdetermined system. But let's see how the pseudo inverse can help us discover what are these solutions and what are the form for these solutions, right? So you start with the matrix A. Again, the first choice or the first attempt is to use theorem 9.2 in computing the pseudo inverse. So we're hoping that A conjugate transpose times A is invertible. So I compute for this product, I'll get this one, which is singular, which is quite sad for us because we need to try the other way around, looking at A star. And it so happened that A star is equal to the matrix 3, 4, 4, 6. Remember the test for invertibility of a 2 by 2 matrix? You just get the determinant. The determinant is what? 18 minus 16. That's equal to 2, not equal to 0. So this guy is invertible. And actually, for 2 by 2 matrices, we have a formula for the inverse, which is this guy, right? So luckily, A conjugate transpose is invertible. So we can use that inverse to compute for the pseudo inverse. So again, from theorem 9.2, here is our pseudo inverse. Actually, this is the unique pseudo inverse. Okay. And then we can use the pseudo inverse to get the solution to our rectangular system, right? So again, X star, the least square solution is A transpose times, A plus times B. A plus was computed to be this guy times the right-hand side 1, 3 in our problem. Then you'll get -1/2, -1/2, 2. All right. Now, is this really one of the solutions? Because remember, we already have a theoretical solution for this, or a solution obtained by hand for this problem without using the pseudo inverse. We said it's -1 minus x2 x2, and then 2. So x2 here is -1/2. So we'll have, so this is 2, so they match. So these two guys match. So that means x is equal to -1/2. And then here we have -1 minus -1/2. So we'll have -1 plus 1/2. So we're going to have -1/2. So indeed, this is one of the exact solutions. If you don't have the theoretical solution at hand, then you can know that this is an exact solution by doing A times X star, right? If you do A times X star, so you multiply this solution vector to our coefficient matrix A, you will get 1, 3, which is exactly the right-hand side. So it is exact because the residual is equal to 0, right? So this is exact. So again, since this is exact, equation 9.5 told us that the solution or all solutions to this system of equation will be of this form, right? And then we know that A conjugate transpose times B is, what is its size? It's 3/1. So this guy is 3/1. So the vector W should be 3/1. So you can pick any 3/1 vector W that you want, put that here, right? And then perform the calculations, you will have another solution. In fact, using all possible 3/1 vectors will give you all the solutions to our given equation, right? So if you want to get an explicit formula for all of the solutions, then you just plug in everything. We already know that this guy is our solution. And then this is a 3x3 identity. Okay, those are the two matrices that we have earlier. Then I am representing W to be W1, W2, and W3. And then if you're patient enough, you will reach this guy, right? This one. So this solution will tell us that any or this computations will tell us that any solution to our to our um, to our system will be of this form. So you think of what the you choose whatever W1 and W2 that you like. It's a little bit different, at least in form, from the solution that I gave you earlier, the simplified version. But if you call this x2, right, then this guy can be shown algebraically to be -1 minus x2. So again, we get an equivalent representation for all the solutions. So that's it. The nice thing about the pseudo-inverse, as illustrated by these three examples, it can give us the exact solution or the exact unique solution, if that is the case for our problem. It can also give us all solutions to a given rectangular system, and it can give us the least square solution, the next best thing we get to the next best thing we get to a close to an exact solution whenever we have an inconsistent system, right? And then in your problem set, probably I'll give you a nice looking matrix A, which will be large. So you might need to use a software to help you compute the matrix A. Probably it's going to be at least 10/4, right? So yeah, I hope you will have your favorite programming language or favorite app with you when you do the problem set, which I will give when. I'll probably give it. I'll write it over the weekend. I'll give it to you on Monday. I'll send you an email about it. I'll also post it in our website under Unit 2B, but the deadline would be April 7, a week after your dashboard with Sir John Murray is due. Okay? Is that good? Okay. Now I'm thinking it's 6:35. I still have 15 minutes. I'm thinking if I can still cover the L curve, but I guess this is very important, especially for parameter estimations if you're doing that using a multitude of of data. Yes, Steven, so you have a question?
Yes, and so I try getting the videos you usually upload, but I don't really know where on our class page you are placing those videos,
Oh yeah.
because I usually see the Joma videos, but yours I'm not seeing.
Uh-huh. Oh, I see. Yeah, let me show you our website. Okay. So let me just stop share from my tablet and then I'll screen share. Hold on, guys. I'll show you where it exactly is. Right, so let me just do it here. Uh-huh. Okay. Right, so you need to go to the page for Unit 2B before you because you'll be able to access the recordings there.
Is that displaying?
Yeah, hold on. I'll share my screen. Okay.
Okay.
Sorry, I'll just share this one. Okay. So you should see now my browser.
Yeah, okay, I'm seeing.
Yeah. So this is the home page. In the left side, you have all the links to the different pages organized by unit. You go to Unit 2B, Fundamental Methods and Techniques in Data Science 2. Click on that. You'll be brought to this page. Right, so the learning materials are here. We used the two bullets under number 1 and number 3. And then the video recordings are here. You just need to, sorry, that will play, but anyway, so that's what will happen.
All right,
So,
okay. Thank you.
all right, you're welcome.
Yeah, thanks.
Yeah, so let me go here. Let me go back. Okay. And then I'll do the same thing. When we go to the next unit, I'll post the recordings on the page for that unit, right? So that you'll all the units are compartmentalized, right? So you won't be confused which one should be watched for which unit.
All right. Okay.
Okay. So quickly, or do I still have the time? Or maybe I'll stop here and probably revisit the L curve regularization before I proceed with the next topics, if that's the case. But Dean Jomar will be handling the class on Tuesday, so I'll be resting for probably a couple of weeks, and then we'll meet again to discuss specific data science problems. But again, the gist of this unit, actually, yeah, and the entirety of Unit 2 is designed to acquaint you with the basic tools, the basic mathematical tools that runs in the background of data science algorithms, right? It might not seem to be very important at this point because probably you're using data science as a tool or data science algorithms like machine learning algorithms, deep learning algorithms as a tool to analyze your data. So essentially, what you might be doing is just feeding your program with data, with pre-processed data, and then harvesting the information, the insights from that black box. But the point of this unit is to allow you to later in life tweak this algorithm so that they will work more efficiently with the kind of data that you have, or if you have a very large amount of data which your computer cannot handle in terms of RAM, you can just use some more efficient algorithms to tweak the block boxes a little bit to suit your purposes. All right. So I hope you learned something new in this unit, at least from the mathematical side. When we meet next, I'm gonna show you. Yeah, let me think. Is that the next chapter for me? But yeah, I know that next time we'll be talking about basic things in data science, all right, or basic data science algorithms. Then we'll work with some datas, with some collection of datas. All right. So, any questions, guys? All right. So, what I want you to do, yeah. So you just need to relax, finish Doc Jomar's problem set because I think you're dealing with large data and having your code to work with large data. So I hope you get it fixed before your deadline. So on Monday, probably at around 8 a.m., I'll send you an email giving you the problem. I'll also post it towards the end of the Unit 2B webpage. And then the deadline would be on April 7th. It will just be exploring LU decomposition. I think I already have a program for the LU decomposition shown you, but I can also share with you my MATLAB code together with my MATLAB code for the QR factorization and my MATLAB code for the Moore-Penrose pseudo-inverse. But actually, you don't need the Moore-Penrose pseudo-inverse code because it's just a one-liner in MATLAB. It's just a\p. But I'll make sure to include those important things in the problem set so that you won't need to go back and refer to the long notes that I shared with you. And if needed, I'll also give you I'll upload the zip file so that the questionnaire is there together with the accompanying MATLAB codes that you need. Unfortunately, I only have MATLAB codes for all of those algorithms I discussed, because I hate programming in Python. All right. So if you prefer Python, you prefer R, so you need to translate the code to that language. All right. Okay. So any questions? Any concerns? All right. So if you're on, thank you for joining me today, guys. The recording will be up probably later tonight or early tomorrow, and yes, I'll see you in a couple of weeks, right? Bye, guys.
Thank you.
sir.
Thank you very much.
Thank you, sir.
All right,
Thank
you're
you,
all
sir.
welcome. Yep, bye-bye.